Right now, the Sun is firing a billion-ton wave of superheated plasma toward Earth. It travels at over 1 million miles per hour. If it's large enough, it could wipe out every satellite in orbit, knock out power grids across entire continents, and plunge hundreds of millions of people into darkness for months. In 1859, a solar storm known as the Carrington event did exactly that to the most advanced technology of the day. Telegraph machines caught fire, operators were electrically shocked, auroras blazed as far south as Cuba. Scientists estimate a modern repeat could cause over $10 trillion in damage. And here's what nobody tells you. We are currently at solar maximum, the peak of the Sun's 11-year activity cycle. In May 2024, the strongest geomagnetic storm in over 20 years struck Earth. Auroras appeared over Mexico, over Italy, over places that hadn't seen them in living memory. The Sun is not the stable, friendly object in our sky we pretend it is. In the next 12 minutes, you will understand exactly what is happening inside it and why the last discovery changes everything. We have been staring at the Sun our entire existence as a species, and yet, only in the last few decades have we begun to understand what is actually happening inside it. Here is a fact that will change how you look at the sky tonight. The sunlight hitting your skin right now left the Sun's core between 10,000 and 170,000 years ago. It spent thousands of centuries bouncing around inside the Sun before finally escaping, and then took just 8 minutes and 20 seconds to reach you. What looks like a simple glowing sphere is a system of multiple distinct layers, each one operating differently, each holding different secrets. We can now see inside those layers by looking at the Sun in light we cannot see. Visible light only shows us the outermost surface, but the Sun radiates across the entire electromagnetic spectrum. Different wavelengths reveal different layers, different temperatures, different phenomena. X-rays show the hottest regions. Extreme ultraviolet reveals the corona. The approach was pioneered by NASA's Solar Dynamics Observatory, launched in 2010, which photographs the Sun continuously across 10 different wavelengths, sending back 1.5 terabytes of data every single day. And now, a new spacecraft has gone further than any instrument before it. On December 24th, 2024, NASA's Parker Solar Probe made the closest approach to the Sun in human history, flying just 3.8 million miles above the solar surface at 430,000 miles per hour, faster than any human-made object has ever moved. For the next 10 minutes, we go layer by layer, from the outside in, starting with the outermost atmosphere, then the violent surface, then the deepest secrets. Parker Solar Probe is only beginning to reveal. Let's go. The surface of the Sun sits at around 5,500 degrees Celsius. Move away from it. Get further from the heat source. Temperature should drop. Instead, it rises. The corona, the Sun's outermost atmosphere, reaches temperatures of 1 to 3 million degrees, up to 500 times hotter than the surface directly below it. Walk away from a fire and you get colder, but move away from the Sun's surface and the atmosphere gets dramatically hotter. For decades, this broke the laws of physics as we understood them. Scientists called it the coronal heating problem, one of the biggest unsolved puzzles in astrophysics. In 2024 and 2025, Parker Solar Probe is beginning to crack it. The leading explanation involves structures called switchbacks, S-shaped kinks in the Sun's magnetic field lines. These kinks carry energy from the photosphere up into the corona, where it converts to heat. Data from Parker Solar Probe's first 14 close flybys confirmed switchbacks are common near the Sun. But in July 2024, researchers showed they don't originate at the surface. They form in the solar wind above it, more complex than anyone thought. Then in 2025, scientists identified the helicity barrier. a newly discovered phenomenon that disrupts how energy cascades through the corona's turbulent plasma, funneling it into heat in a previously overlooked way. It may finally explain why solar wind protons are hotter than electrons, a mystery that had stood for half a century. The corona can also be seen by the naked eye, once in a great while. During a total solar eclipse, when the moon precisely covers the photosphere, the corona blazes into view, a white, ghostly halo stretching millions of kilometers into space. One of the most extraordinary sights a human can witness. Stay with me, the sun's surface features are even stranger. There are three types of solar eruptions you need to understand: solar flares, coronal mass ejections, and solar energetic particle events. A solar flare is a flash, an explosion of electromagnetic radiation, X-rays, ultraviolet, radio that travels at the speed of light and reaches Earth in 8 minutes. A large flare disrupts radio communications and GPS signals almost instantly. A coronal mass ejection, a CME, is different. It is a physical cloud. Billions of tons of magnetized plasma hurled into space at up to 3,000 kilometers per second. CMEs take 1 to 3 days to reach Earth. When they hit our magnetosphere, the results range from spectacular auroras to catastrophic infrastructure failure. In May 2024, a series of powerful CMEs struck Earth, the strongest geomagnetic storm in 21 years. G5, the maximum category. Auroras over Florida, Mexico, southern Europe. GPS-guided farm tractors went haywire across the American Midwest. Satellites dropped in altitude as Earth's atmosphere expanded from the heating. The third type: solar energetic particle events. Streams of high-energy protons accelerated to near-light speeds. The most dangerous for astronauts and spacecraft electronics. In June 2025, Parker Solar Probe identified a new source of these particles closer to the Sun than anyone previously knew. The Sun is not just our light source, it is the most powerful space weather engine in the solar system, and we are living through its most active phase in a generation. But we can now see these storms coming. Keep watching. In visible light, the photosphere looks smooth, clean, sharp. Zoom in and it boils. The entire surface is covered in cells, around 1,000 kilometers wide each, called solar granules. These are the tops of enormous convection currents. Superheated plasma rises from the interior at supersonic speeds, over 7 kilometers per second, spreads across the surface, cools, and sinks back down at the dark edges of each cell. Each granule lasts about 20 minutes. At any moment, roughly 5 million of them cover the Sun simultaneously. The collision of plasma crashing back down creates shock waves. Scientists use these to peer inside the Sun using helioseismology, the same principle as a doctor's ultrasound, but for a star. Now, sunspots. They appear darker because they are cooler, around 3,500 degrees versus the 5,500 degree surrounding photosphere. But that's only by comparison. They form where the Sun's magnetic field is exceptionally powerful, strong enough to suppress the convection that brings heat to the surface. The critical connection. Sunspot groups are directly linked to solar flares. The same magnetic region that produces a sunspot cluster almost always produces the flare above it. Watch a sunspot forming. You're watching a future explosion building in slow motion. Just above the photosphere is the chromosphere, a thin layer of pink plasma, 1,700 kilometers thick, filled with features called spicules. Millions of plasma jets firing upward at 100 kilometers per second, 282 times the speed of sound. They reach lengths of nearly 10,000 kilometers and vanish in 5 to 10 minutes. Scientists couldn't explain them for decades. In 2017, a research team discovered the answer. Neutral particles, particles without electrical charge, were giving the magnetically constrained plasma the extra buoyancy it needed to escape upward. One missing ingredient that changed the entire model. And yet, despite all of this, we have only scratched the surface, literally. The photosphere is the deepest layer scientists can directly observe. Everything below it, the convection zone, the radiative zone, the core, is known only indirectly through seismic models and mathematical inference. The core itself, where hydrogen fuses into helium at 15 million degrees, generating all of this energy, remains beyond direct observation. We have flown closer to the Sun than any spacecraft in history. We have photographed it in 10 wavelengths of light, and there is still so much we cannot see. We started with a warning. The Sun fires plasma at Earth. It has done so for 4.6 billion years. It will continue for another 5 billion. But we now understand it in a way no generation before us has. We have looked at it in 10 wavelengths of light. We have flown a spacecraft through its atmosphere at 430,000 miles per hour. We have discovered why the corona is hotter than the surface. We have mapped the connection between sunspots and the storms above them. And we have identified plasma jets on its surface that nobody could explain for a century. The Sun is the reason everything you have ever known exists. And every close look reveals it to be stranger and more surprising than we thought. If you want to follow every major discovery in space exploration as it happens, subscribe. We cover the biggest stories the moment they break. There is so much more out there.